Hello again. This video is part 2 of our earlier video entitled Space Navigation. Navigation in space requires that you know velocity and position relative to a predefined inertial coordinate frame. Change in velocity is calculated by integrating measured inertial acceleration over time, and change in position is calculated by integrating velocity over time. I show the first integration logically in the following equation, which must be solved iteratively, once for each defined time step, delta t. First, the new velocity is equal to the old velocity plus any change in velocity, delta v, since the last time it was calculated. I show this in equation form on my right. But acceleration, a, is the change in velocity divided by the change in time. Therefore, we can rewrite the previous equation like I now show. If, on board the spacecraft, we continuously and iteratively solve this last equation based on continuously measured acceleration at precise time increments, we can calculate the change in spacecraft velocity as time progresses. But how is acceleration measured? One way to measure acceleration is to use a weight of known mass held in position using springs, one for each coordinate axis. When the mass is accelerated, inertia causes it to depress or stretch the springs. Remember that inertia opposes any change in a mass's velocity, and that inertial force is equal to the negative of mass times the resulting acceleration. Also recall that force is equal to the spring constant multiplied by the spring's displacement. I summarize all this in the equation that I now show. Therefore, we simply measure the spring's displacement in each axis and use it to calculate the inertial acceleration vector. Then we must integrate this measured acceleration to find the change in velocity in inertial space. I show all this in the following iteratively solved equation, where F is the inertial force exerted on the spring due to acceleration, K is the spring constant, D is the mass displacement, and M is the mass of the weight at the end of the spring. This equation must be solved for each step in time, delta t. Likewise, position is solved for by integrating velocity for each step in time. Smaller time steps result in more accurate results. There are now more modern ways of measuring acceleration, but using a mass and spring is more intuitive. It should be obvious to you that accurate calculation of position and velocity also requires an accurate time standard on board the spacecraft. If you find this video useful, please give it a like. If you find this YouTube channel useful and want to be notified when we add more videos, click on the notification bell. Finally, leave a note if you have comments or requests for new videos. Goodbye.